Right, in this video I'm going to look at introduce a slightly different way of solving this problem, Pythagorean triples. Let me review the first two methods that was introduced in the earlier videos. The first one was looking at observing the difference between this number, maybe the longest legs, and to the hypotenuse, difference between these two. And we were able to parameterize this integer primitive solutions in terms of t and in terms of additional integer parameters. And we noticed that this is homogeneous polynomial terms, so actually all the integer solutions is equivalent kind of to the rational solution of the simpler curve, which is unit circle. And I introduced not about the solving the full solutions, but kind of introduced the structure in the solution set. Namely, that was a binary operation that was defined on this unit circle. So one advantage of this operation thing is that if you have a couple of solutions or a single solution, using this operation to generate more and more solutions. Just to distinguish all these different methods, I might call this one is more arithmetic approach, and I'd like to call that one more algebraic approach. So I'd like to say that what we're about to introduce here is more a geometric approach. So here's our unit circle. This method, I think it's first introduced as a method of sweeping a line. So here's the first direction. Suppose we have a point on here in the unit circle with x-coordinate x and y-coordinate y, and they're all rational numbers. And on here, that's what we're looking for. Then if you draw a straight line from here to there, like this, and if I continue it here, and we think about this straight line, and what are we going to think about it? And the idea is just think about the slope of this line. So here's the slope of these two lines, and you know how to calculate the slope of the line, which is namely y-coordinate, difference of y-coordinate divided by x-coordinate. That's the slope. So the key idea here is geometrically represented as if you, whenever you have a rational points x comma y, and playing with this one rational solution, you realize that this is also a rational solution. We happen to know it's kind of easy pointed out here that we associate this one with this quantity, which is also a rational number. The y is a rational number, and x minus 1 remains the rational number. So we're associating this one with a rational number, which is here the slope. But if you forget about the slope and what we have, just focus on what we have accomplished here, one point associated with the rational number. And the way we associate it here is quite algebraic and keeping the rationality. That's the key point. So rationality here. So if you have these, so this is usually the idea of a map. So this idea comes from algebraic geometry, and I can say honestly with confidence that algebraic geometry is all about maps, and you have an idea and you have properties, and they translate everything in terms of maps, and that's pretty much what is going on, and not only in algebraic geometry, in many other parts of pure mathematics. So we created a map, some sort of rational solution set. Let's represent that with a z0, and then we associated each of the rational solution with a rational number in here, rational number. Okay? So let's write this one down more correctly. I'm going to define the z, the set of all rational solutions to this unit circle, but there's a little bit of problem in this definition with this particular problem in here. If you happen to choose this rational point to be this point itself, 1 comma 0, intuitively that we should define that particular line to be this vertical line, kind of tangent, if you continuously approach that, and that tangent line happens to be the vertical. We don't define slope to a vertical line. So why don't I define z naught to be all the rational solutions like this, but x is not equal to 1. That forces when x is 1 and only choice for y value, it's from this picture is clear that y equals 0, but you can also prove that. So we define this one before we clearly define this map we're talking about. So we define now, and secondly, that's the first thing we define it here, and secondly, we define a map. We're going to call this map named m. M came from the slope, the z0. Everything now you can see has well-defined slope. Whenever you have a point in here, we can define the slope as a number. This is given by following formula where p has x coordinate x and y coordinate y, the rational numbers. Then we define it like this: y divided by x minus 1, that since x is not equal to 1, this makes perfect sense. X's denominator is not going to be 0. So we define this map. Here, one remark I'd like to make here is this map is not anything special about this unit circle. You can imagine if you happen to look at more complicated curve than this, and if you happen to have one rational point in here, that's a key point. We still requires everywhere we go with this technique, we still need one single rational solution in there. Once you have the rational solution, you can always draw this line and associate it with this slope in here. So this definition is like this map M that we have defined here can be defined a lot more general curves, a higher degree, as long as we have this rational point. Here's our first part of the slide. Let me emphasize it here. The thing that we were looking at the very beginning was a parameterization, and you can also pull out the parameterization for rational solutions as well. So let me go back down, come back in here, and this is our earlier slide. From this picture, I think it's quite clear from the picture that we have one-to-one correspondence between each of the point and slope that is associated with it. So if you have one point in here, then it's going to correspond to some sort of slope. And if you think about other points, it seems like it's clear that whenever you have two distinct points on the circle, there will be always a different slope. So we kind of exhibited or observed that m is actually one-to-one. And again, when you prove it, we try to not rely on this visual information and try to do as much algebraic as possible. More interesting part in here, this function m, for given each point to associate the slope, it's actually the surjective, and that's the interesting part. Like this here. This one-to-one and surjective indicates that this map is actually bijective, one-to-one and surjective. So one way to establish this one-to-one property and surjective, every point in here, I didn't really explain what the surjective means. It means if you choose any slope in here, which as long as a rational number, there will be a point that such that slope with that point and this 1, 0 is the arbitrary rational number you chose in this right-hand side. So every slope is realized as a slope of 2 points on this unit circle. It's two things that this set theoretical description I just did, every point is realized and no 2 points have the same slope, and that's the summary of these two things. That doesn't quite explain a nice algebraic inverse map, but the fact is that this kind of indicates that maybe there is a nice, this indicates that there is an inverse map. What we're trying to say is that inverse map in here going from to there, from Q to a point, is actually algebraically very nice. So we have nice algebraic, actually polynomial coordinate functions that describes going from here to there. So if I describe this one as t, and we're describing each of the points with this t, that sounds like parameterization. That's exactly the idea of the parameterization. Here described it in terms of maps. And here the more strong effect is that the inverse map, that is going from each of the slope, maybe represented by t, is going to correspond to exactly the 1 point on this unit circle. So each of the coordinates that we're describing in terms of this slope is rational functions. So that preserves rationality, and this is a really nice result. Right? Not only it's saying it's invertible, that inverse map is actually preserving the rationality. So if you have t there, and that's going to be not only is a rational numbers, but it's given by a rational function. So here I wrote it down. This map description is really explaining the existence of aparameterization. So before we prove about this map or know more about this inverse map, let me introduce this visualization of associating these points with a slope. So here's a line, possibly this is a rational points, and we're looking at the slope of this line. The line itself is there, so you can think about the slope, but we can turn that slope into a number here, or represent it as a length of something. So because this is a 1 unit, this height here, or this distance right here, I'm drawing a thick line, that magnitude of that quite represent the slope of this line. Right now the slope of this line looks like a negative number, but if you read the y-coordinate of that point is not really a negative number, but its magnitude, y-coordinate there, its magnitude is actually this correct magnitude of the slope of this line, because the 1 unit in this rise part is moving towards the left. So if you interpret it like this, that really represent a magnitude of the slope of this line. If you have a point over here, then you can see that line that intersects it here, and that magnitude right there represent the correct magnitude of this positive slope of this line. If you happen to have a point over here, then you can see that's going to be intersecting y-axis over there, and that length right there is the, if you turn that into a positive number, and that's the slope of this line. So it's intersecting y-axis and representing exact amount of slope as a y-coordinate here. I hope you find this one similar to the Riemann stereographic projection of the sphere down to a plane, and this is exactly the same idea. It's just happening in 2-dimensional space rather than 3-dimensional space. So that Riemann stereographic projection is giving us this idea of parametrization, because the line intersects this circle exactly at 2 points, and 1 point is affixed at here, and that kind of happen to parameterize the other point. So again, I think I said that degree 2 and 1 fixed point gives you unique association with the remaining point. That's the idea behind this parameterization, actually, if you think about it. But we haven't proved this surjectivity part, so, or this whole thing. So we're going to take that. More reasonable question you ask when you look at this function is really whether the function is surjective or not. But once you think about it and try to formulate, and this is the better thing to prove, and it has more information. So here is the statement: the slope map is actually invertible. Not only it's invertible, the formula of this slope function, inverse of the slope function, is given by rational functions. So here I summarize what we wanted to prove. That'll explain everything that we were talking about. M is the slope function. This is all rational points on the unit circle except 1, 0, and we have this formula. And we want to prove what the inverse of this thing is. So we start with t is this representing the slope, and later on it'll serve as a parameter to parameterize all those points in and here. So that's why I'm using t in there. So let's think about m inverse of t. One is this going to be this point P, which is in general x and y. This is not a random point, but this came from unit circle in here. Okay, so we're going to use typical inverse method of computing the inverse. This is namely, if I represent this one as a P, MP being a T, and that's what we're looking for. So here, P is x and y, knowing that it's coming from this unit circle. So we have y divided by x minus 1 equals t. That we want to solve this one together with that unit circle condition right there. So in this context, the t is given, right? You have to understand everything is here in the letter. You might forget the context. T is given, and we try to figure out x and y such that x and y satisfy this unit circle equation. So I think it's natural to turn that equation right there into a polynomial looking equation. So t times x minus 1, and this x and y are not totally independent. It is related like this: x squared plus y squared equals 1. Because it's already y is isolated like this, and then we're going to make a substitution, and then we'll solve for x. But I hope you understand where this x minus 1 is coming from. X minus 1 is coming from that fixed point, which is happen to be the rational. And this part of the technique is true for all the other conic sections. We happen to know one rational solutions, and we're comparing other rational solution with this one together with the line. So it turns out technique of substituting this one into something else like z really helps us to handle the factorization and figuring out what the other x-coordinate of the intersection thing is. So that's what we're going to do. So we make a substitution, so the rest of the part gets really easy. And this technique is especially useful when you look at other twists of a circle, or namely ellipse and all the other conic sections. So this equation, actually, if you make this substitution, z equals x minus 1, then we have new equation. Y is going to be t times z, a lot simpler. And x, if you solve for x, and in here you can see z's x is z plus 1, so we have z plus 1 squared and y squared equals 1. So whereas y is substituted here, so that z plus 1 squared plus y is t z squared, and here like that is equal to 1. So solving for the z will eventually equal to the solving for x in here. Right here, if you expand those, you can see that z squared plus 2z survives, and this 1, and after you square it, and this one cancels, so you only have t squared z squared equals 0 after you cancel that out. So this is the advantage, where because all the z's are common, and this is now an quadratic, but you can easily factor out the z part, and that's the benefit of rewriting x minus 1 with a z. So if z is non-zero, this is not quite what we're interested in. X equals 1, we're looking for other points. So if z is not equal to 0, then you can cancel those z, which is same as factoring out. And here, let me first go in and simplify this one. 1 plus t squared z squared plus 2z equals 0. So you can see that we've seen this a lot in previous videos, and shows up everywhere. So if you cancel those z, and we have 1 plus t squared z plus 2 equals 0. So if you solve for z, then it's negative 2 divided by 1 plus t squared. So because z and x are related linearly like this, is a simple matter of solving this thing for x by just going back to a substitution. So if you add 1 to the other side and put it into a common denominator, and this is what we have, x equals 1 plus t squared in the denominator, and up there is a t squared minus 1. Okay, so it's 1 plus t squared going up there, and you cancel with -2, that's correct. So that's what x is, the other x coordinate. So let me go back and show you the picture. This is the x coordinate here, and we were calculating the other x coordinate. And this is the formula, and what you have to pay attention in here is that t came from the rational number here, and x coordinate end up in rational number. That's the key part. Why did that happen? Why is this rationality was obtained? Is because the equation we're eventually dealing with in here, when you substitute y equals this linear in x, you end up at degree 2 equation in x. And one of the solutions in the circle is 1, that's rational numbers, and it's degree 2, that forces the remaining x being rational. Right, that's what happened. So degree 2, 1 point being rational, the other one must be rational as well, if it is appearing on this line, which is degree 1. Right, that's the main ingredients that makes things work. Now, what is y? Y here is t times z. I think that's easier formula to use than going back in here, subtract 1 again. So what would z? Z was -2, t is here, times -2 divided by 1 plus t squared. So I think we obtained this formula back again, which we obtained it somewhere early in the video. So this is rational parameterization of all the points on the unit circle except 1, 0. So formula of m over t finally is the x coordinate. It's going t squared minus 1. I'm going to write it like this, t squared plus 1, and a negative 2t divided by t squared plus 1. So let me point that out, that this technique actually works for all the conics. If you look at it here, if you happen to know one point, one rational point, you can just draw this line, and at most it intersects at one more point because of the degree that we're playing with, the degree 2. All the conic equations given in degree 2, and you can isolate y or x because it's on the line, and if you plug it in there, degree 2 polynomial in one variable, and you happen to know already one solution there, therefore it forces the other one to be rational numbers. So you can always construct this map using the same idea of a slope, straight line, then you'll be able to find the inverse function. That, if you look at this map in here, all the rational numbers going to something, that's exactly the idea of the parameterization that was started with in here in terms of rational variables.